All right, this tape is on linear equations. Now let's get some things straight about it. This is linear equations with one variable, one equation. One variable, one equation. Now what a linear equation means, first of all, is that the highest power of the letters in here will be a 1. If you had an x squared, then it would not be a linear equation. So linear equations are equations where the powers of the letters are the first power. We're only going to work with equations that have one letter in them, and we're only going to work with one equation at a time. All right, now, when we work with linear equations, we have three things that can happen. One, we can get one solution, one exact solution. Now, know what you're trying to do. Here's what you're trying to do. You're trying to do just like second grade arithmetic, where they had 5 times a block equals 10, and they got the student to figure out what went in that block. What goes here that will make 5 times that equal to 10? That's all we're doing. We're just putting letters now, and we call this algebra. So we go solve this equation, dividing both sides by 5, and we get x equals 2. Now listen again. Take this answer. Go check it, see if it works. If I go take 2 for x, put it in the original equation, does it check? Yes, it does. Therefore, a linear equation with one variable can have one solution. Or, hey, let's look at another example. The second case that could happen in a problem, when you start making up equations and writing down letters and x and numbers, then these things can happen. The next case is, all right, let's say I have a 5x plus 2 minus the parenthesis is equal to 2x plus 8. Now let's learn here again the algebra, the arithmetic, the methods that we use. And the method is we remove parentheses. So if we remove a parenthesis, we multiply everything inside by what's directly in front of it. So a minus times this would be a minus 3x. So removing that would be a minus 3x. Then the minus times a minus would make this a plus. And so now we have 5x minus 3x. We add the x's to the x's. We get 2x. We add the numbers to the numbers. And we get 8. And look what happens. We get an equation that has the same exact thing on both sides. What that means now is, look, we can use any number. If I put 0 in here, we get 8 equals 8. If I put a 1 in here, we get 10 equals 10. Put a 2 in here, we get 12 equals 12. Put a 3 in here, put a minus 5 in here. Put any number you want to put in here. Any number you want to put in here, this side will equal that side. So it comes out to be what's called an identity. This equation becomes an identity. It's true for all numbers. So that's what can happen. All right, the third thing that can happen, and the thing that you need to check on, the reason you need to check your answers on all your homework problems when you deal with linear equations, is the idea of no solution. Now, and we're going to learn how to do this later, but when you go solve all that, you'll get an answer of x equals 1. And that looks good. But if you go plug a 1 back in the original equation, you put a 1 here and you got 2 over 1 minus 1, which is 0. 2 divided by 0? Nope. Cannot divide by 0. Cannot divide by 0. Therefore, this is not a correct answer. Even though your arithmetic and all your algebra worked, it means there is no answer to this original equation. There's not a number that you can put in the original equation here that would make the left side equal to the right side. So therefore, it has no solution. So let me say one more time. When we're working linear equations, we can either get exactly one solution, and sometimes two. We can get a definite number. Well, just get one solution, Get one solution, or many, or none. All right, let's now look at example 1. And now what we're doing is, and this is what's most important about this tape, listen and learn the mechanical process of solving for x in a linear equation. All the arithmetic, algebra rules we use. Pay attention. All right, first of all, we remove parentheses. So 3 times this would be 12. 3 times this would be a minus 15x. A minus 2 times x is a minus 2x. And a minus 2 times a plus 4 is a minus 8 is equal to 21. Remove parentheses by multiplying what is directly in front of the parentheses. Everything that's inside. All right. Now the next concept is to add x's to x's, apples to apples, oranges to oranges, numbers to numbers. So we will add the x's, and so we get a minus 17x. We add the numbers. 12 minus 8 is a plus 4 is equal to 21. All right. Now the next rule is get the x's on one side of the equation sign and everything else on the other side. Get the letter that you're looking for on one side of the equation, the equal sign, and everything else on the other side. That means we must move the 4 across. Now please learn this for sure. Learn the way I'm going to teach it. It works all cases. Don't be using that, well, if I move it across, I change the sign and all that garbage. You do it just like this. If you move anything across the equal sign, you do it by doing the opposite operation. This 4 is added, so we will subtract 4 from both sides. So we have a minus 17x is equal to 17. Now, okay. Now we want x by itself. Okay, we want x by itself. So what do we have to do to get rid of the minus 17? Well, some people say, well, move it across. No, no, no. Yeah. Now what we want to do is to get rid of it or move it across by doing the opposite operation. How is the x and the minus 17 connected? It's connected by multiplication. Therefore, we divide both sides by minus 17. So this divides out, leaves us x, 1x, and this divides out and leaves us a minus 1. All right? Now, I hope you pay attention to the mechanical rules of algebra, and that is to move anything across. That's the way people talk about it. I want to remove this across, or I want to get rid of it on this side. The way you get rid of something on one side of an equation is to do its opposite operation. Up here it was added, so we subtracted the 4. Down here it was multiplied, the 17 was multiplied, so we divided. Do the opposite operation. That's going to be crucial when we go to some of the examples and some of your homework that have letters and not numbers. You'll really get yourself confused if you don't follow this rule. All right, last thing on the problem now is to always check your answer. See, this could be a case where it's no solution, so we must check our answer. So let's go back and plug the minus 1 into the original equation where the x is. So going back up here, we will have 3 times 4 times a minus 5 times a minus 1 minus 2 times a minus 1 plus 4 is that equal to 21? Well, let's see. This would be 3 times 4 plus 5 minus 2 times 3. Well, this is 9. 3 times 9 is 27 minus 6, and sure enough, it is equal to 21, and therefore, that is our solution. All right, example 2. Okay, example 2. What's the rule? We get rid of parentheses. So we multiply everything inside here by plus 8. So we get 8x plus 16. Multiplying everything in here is a minus 6x minus 3. And multiplying everything over here by 2, we get 2x plus 10. All right, next rule is add x's to x's, numbers to numbers. So 8x and 6x is 2x. 16 and a minus 3 is 13. 2x plus 10. Now, what's the rule? The rule here is now to get all the x's on one side, everything else on the other side. All x's on one side. It doesn't make any difference which side. All x's on one side of the equal sign, everything else on the other side. So this is a plus here, so we'll subtract 2x from both sides. And adding a minus 2 to a plus 2, that drops out, and we get 13 equals 10. And that can't be true. Therefore, this is a no solution. Okay, it came out that there wasn't any numbers that made it work. All right, now let's go to the next example. All right, now we have denominators. We have denominators. So what we're going to do is forget all those other rules and say the first rule here, when we have denominators, is to multiply everything by the common denominator. I didn't say lowest, just a common denominator. We want to multiply all of this and all of this and all of this by a common denominator, so we will not have any more denominators. Now, it doesn't have to be the lowest. The lowest will make your numbers a little smaller, but it doesn't have to be. So what's a common denominator? 12? No, that doesn't go in 12. 24? Yeah, that goes. Okay, 24 would work. 48 would work. 72 would work. A lot of different numbers. So let's just pick 24. So what we want to do is to multiply everything by the common denominator. Now, listen to this. Whenever you have denominators, what I would do first is put any binomial in parentheses. Where you have something added or subtracted, put it in parentheses. Even if it's in the denominator, put it in parentheses. All right, now I'm going to recopy this. So we're going to write down and multiply by the common denominator. Multiply by the common denominator. Multiply by the common denominator. And look what happens. This 4 will divide into this 6 times. So we have 6 times 3x plus 4. This 8 will go into this 3 times, so we have a minus 15x. This 6 will go into that 4 times, so we have 4 times 2x plus 4. And look what we are. We're back to last examples. We're back to example 1 and 2, which says remove parentheses. So removing parentheses, we have 18x plus 24 minus 15x is equal to 8x plus 16. Now, what's the rule? The rule is to get all the x's on one side and numbers on the other side. So, hey, let's combine this. 18x and 15x is 3x plus 24, and 8x plus 16. Now, pay attention. I said this once before. If we don't have to have x on that side, we can have x on this side. Let's don't move the biggest x and get a negative number. Let's move the smallest x to the other side. So what we want to do is to subtract 3x from both sides, and that gets rid of the x's over here, and now we need to get the numbers over there. So we'll subtract 16 from both sides, and look what happens. We get that drops out, and we get, oh, that's 8 positive, and this is 5x. And that drops out. Okay, that's nice. So we now have 5x equal 8. So what's x equal to? Well, we want to move that 5 across, or we want to get rid of that 5. How's it connected? It's connected by multiplication. Therefore, we divide both sides, and the 5's drop out, and we get x is equal to 8/5. And now, don't forget, you need to now go check your answer. Go put that back in the original problem, simplify getting common denominators and all that stuff, and check to see if it works. Or in your homework, look in the back of the book. Check it right quick. All right, let's go to example 4. Okay, example 4. What did I tell you the first thing to do? Well, I said if we have denominators, no, what I said is if we have binomials, put them in parentheses. But now I'm adding another rule. And the other rule in this is If you have an x squared in here, you need to factor that into two parentheses by the FOIL method. Okay, so we want a plus 3 and a minus 2 here. First times the first, last times the last, inside, outside. Checks out. So now we progressed another rule, and that is if the denominators can, not the numerators, if the denominators can be factored, factor them first. Because we need to have it all factored so we can decide what the common denominator is. All right, now we have it factored. Now we're back to denominator. So we want to figure out what the common denominator is. Well, the common denominator is I have this factor, I have this factor. That's the same one. I have that one. So my common denominator is x minus 2, x plus 3. All right. So the rule is then multiply all of this up here by the common denominator, multiply all this by the common denominator, multiply all this by the common denominator. So let's rewrite that. So we'll have 1 over x minus 2 times x minus 2 times x plus 3 plus 3 over x plus 3 times x minus 2 x plus 3 equals 4 times x plus 2 x minus 2 x plus 3 times x minus 2 x plus 3. Okay, multiply everything on the top here by the common denominator. Multiply everything. And now look what happens. This one drops out with that, and we have 1 times this, so that's x plus 3. This drops out with that parenthesis, and we have 3 times x minus 2. And both of those drop out, and we have equals to 4. And look what we are. We're now back to example 1 and 2. So we'll write down x plus 3 plus 3x minus 6 is equal to 4. Adding the x's, we get 4x minus 3 is equal to 4. And so we get 4x is equal to 7. How'd I get that right quick? Well, this is by subtraction, therefore I add 3 to both sides. And now what I do, this is connected by multiplication, so I divide. So therefore x is equal to 7/4. Then we go back and check that in. Go back and put a 7/4 in the original problem, get common denominator there, and check it out. Okay, now let's look at 4 more examples. All right, example 5 has 7 over 2x plus 1 minus 8x over 2x minus 1 equals minus 4 over 1. So what I say? Put these in parentheses. What's our common denominator? Well, there's a different factor, and there's a different one, and 1's 1. So our common denominator is this times that. This times that. This denominator times that denominator times 1. So our common denominator is this parenthesis times that parenthesis. All right, what do? We multiply everything up here by that common denominator, everything here by that common denominator, and everything here by that common denominator. So let's look at the next line. So we'll have 7 times the common denominator. Well, this parenthesis divides out that parenthesis. So we get 7 times 2x minus 1. This parenthesis divides out that parenthesis. So we get minus 8x times 2x plus 1 equals, nothing divides out, so we have a minus 4, we have a minus 4 times. Now, let's go back up here and do this. This is where we use the FOIL method, or multiply it out, whatever way you're taught. So the first times the first is 4x squared. Last times the last is a minus 1. And the inside is a plus 2x. And the outside is a minus, that adds up to 0. So we don't have a middle term here. So I'll just move this over a little closer. So we have 4x squared minus 1. Hey, well, now we're back to the beginning of all these, and that's to remove parentheses. So let's start over here. This would then be 14x minus 7 minus 16x squared 8 times a 2 is 16. X times x is x squared. Minus 8x times a plus 1 is a minus 8x equals a minus 16x squared plus 4. Minus times a minus is a plus. A lot of us are careless here now. But don't forget, that's a minus 4 times everything inside. Now what do we do? Well, we have a minus 16x squared, and let's get that over to that side. So we'll add 16x squared to both sides. And at the same time we can do all this, let's add the x's. 14x minus 8 is 6x. We have a minus 7. This drops out. Okay, over here this drops out. We have 4. So now we want to get the 7 across by doing the opposite operation. It's subtracted over here, so we'll add it. So we get 6x is equal to 11. Now we want to get the 6, get rid of the 6, so it's connected by multiplication. Therefore we divide, and so x is equal to 11/6. All right. So let's see, that looks all right. So let's go to the next example. Okay, going to example 6. We have 5 plus ax is equal to 12. All right, here we have letters. We have letters in here, and that's what I was saying. We need to learn to use our rules. All right, so here we go. We want to get all the x's to one side, so we want to get this x to that side. So we have to add this. So we add bx. Well, that doesn't go underneath that. This is an ax, that's a bx. That doesn't go together. But we still go ahead and add that to both sides. So we have 5 plus ax plus bx. We can't combine them. We just write them down, both of them. And over here, this drops out and gives us 12. All right, well, now we got the x's on one side. Now we get rid of the numbers. So we want that over there. It's connected by addition, so we subtract it. So we have ax plus bx is equal to 7. Now, new rule here. We have an x times a and an x times, so we factor out an x. So we have x times a plus b is equal to 7. Okay, now what's the rule? We have x connected by multiplication. Therefore, we divide both sides by a plus b, and this divides out, and so we have x is equal to 7 over a plus b. And it just works out that way without us thinking it out or making sure. Is just if you go by the rules, that if you want to get rid of something on this side, you do the opposite operation with it. So we get x equals 7 over a plus b. All right, let's look at example 7 now. Okay, example 7. Hey, all letters, no numbers, all letters. So we'll follow the rule. Rule is common denominator. This is over 1. So our common denominator is L. So I'll multiply everything by L. Everything by L. These drop out. So we have HL is equal to KA times T2 minus T1. Now, wait a minute. We've got to make a decision on which letter we're solving for now. So we're solving for T sub 1. We're solving for this letter. So what's a good step there? What I would do, I guess, is to go ahead and multiply this out. I'd kind of stay with our rules. So this would be KAT2 minus KAT1. All right? Now, what do we do now? We're solving for T1, so we're going to get it all by itself on one side. So I'm going to move it across. I'm going to add this to both sides. And I'm going to subtract this from both sides. Okay, because I want it on this side. So doing that, that drops out. And so we have KAT1 is equal to KAT2 minus HL. And we're following the same rules we've done before. We just got all letters, no numbers. All right, now we're solving for T1. How's this connected? By multiplication. So we're going to divide both sides by KA and just put this all in the denominator. And this divides out, and there's our answer. Becomes a simple task if we will simply follow the rules of moving things across. Quit thinking about moving across, changing the sign, or things like that. Just move, get it rid of it on one side, but doing the opposite operation. All right, let's look at the last example now. Okay, the last example is, again, a denominator, so we'll put parentheses around it. Again, we have to factor. So our common denominator is x minus 2 times x plus 2. So we multiply this by x plus 2, x minus 2. We multiply the 3 by x plus 2, x minus 3. We multiply the 6x by x plus 2 minus 2. What happens over here? This one divides out. We get x plus 2. This divides out. We get 3 times x minus 2. Both of these divide out. We get just a minus 6x. So we get x plus 2 is equal to 3x minus 6 minus 6x. So we have x plus 2 is equal to a minus 3x minus 6. And so what do we do here? This is subtracted, so we'll add 3x to both sides. And then we'll move the 2 across by subtracting it from both sides. And we get 4x is equal to a minus 8. X then is equal to minus 2 by dividing both sides by 4. Minus 2. X is a minus 2. Okay? Beginning of the tape, when we worked examples, we said, always check your work. So now watch. We will now take this and go back and plug it in the original equation. So we get 1 over a minus 4 equals 3 over 0. Ooh, 3 over 0. And here we would have a minus 12 over 0. No. Cannot divide by 0. Therefore, the answer x equals to a minus 2 does not work in the original equation. And so this is called a no solution problem. Now at the top of the example it says extraneous root. And this is what this means. It so happens that when you come and take an equation and you multiply some things into that equation, you multiply both sides by something, then you can introduce what's called an extraneous root. It's an added root. It works this equation. It works the one you simplify for multiplying, but it doesn't work the original equation.
I believe that equations are most useful in solving word problems. Now, the word problem idea is the most intimidating thing probably in mathematics. Let's look at how a word problem, though, transforms into an equation. Here's one way to look at it, and it's through a method called mathematical modeling. Mathematical modeling involves taking a verbal description, which is the problem itself written in words, and write down a verbal model. Now, that verbal model is nothing more than your understanding of the relationship of the items involved in your word problem. You see, it's kind of an equation written in words. And from the verbal model, we go into the mathematical model, which is the equation itself. Now, this is one way of approaching word problems. Now, let's see how this works out. Consider this word problem. You have accepted a job for which your annual salary will be $24,740. This salary includes a year-end bonus of $500. If you are paid twice a month, what will be your gross pay for each paycheck? Now here we've outlined our problem, It says annual salary, $24,740, bonus $500. We're paid twice a month. How much is each paycheck? Well, let's just write down what we intend to know, or the relationship that we understand here. We know that our annual salary is composed of 24 payments times each paycheck. Now, why 24? Well, because we're paid twice a month. 12 months in a year, paid twice a month, we get 24 paychecks. So it's 24 times each paycheck plus the year-end bonus. All right, now, this is that verbal model. This is kind of the halfway house on our way to solving our equation, or building an equation to solve this problem. Now, what we need after our verbal model is some representation for each item we have in regular words, you see. We need a label for each item. Well, annual salary, the label for that is the $24,740. And each paycheck, well, we need a variable to stand for that. We don't know the value of it. We let some letter stand for it. So let's let X stand in for each paycheck. Now, usually we would write that somewhere, let X be equal to the paycheck or whatever. But we take our verbal model and we build labels for each item in it, and then we are building our equation, you see. So we're letting X stand in for each paycheck, and the bonus was given earlier as 500. So now we have built our equation. And if we solve the equation, we find that X is $1,010 for each paycheck. The point here, though, is to understand that in this development of the solution to a word problem, what we're doing is we're going from the word problem itself to an intermediate step called a verbal model. And from the verbal model, we are really building an equation. It's kind of an equation in word form. And then from there, we build the real mathematical model, or the equation, and we solve the equation to solve the problem. Suppose we have this situation. Suppose we have a job that pays $8 per hour, and then that job pays $9 per hour in 2 months. What percent raise will be received after that 2-month period, you see? Well, again, to solve the problem, we sort of write down our understanding of what this is saying. We write down a relationship, an equation of some kind. What is equal to what here? That's what we're searching for in this problem. All right, so our verbal model might be something like this. Well, we want to figure out what percent we're getting in our raise. So our raise, then, is what percent of the old wage. That's really what this is asking for. The raise represents, or is equal to, has the same value as, you see, the raise is what percent of the old wage? Well, the raise, the amount of the raise from $8 to $9 is $1. Now, what percent? Well, that's what we're looking for. We'll let a letter stand for this, where I'm letting N stand for that amount right now. Of generally means times of the old wage. Well, the old wage was $8. So a raise of $1 represents what percent of the old wage? Dividing on both sides by 8, we find N to be 1/8. Now, I'm writing all this out here because it's important to notice in a problem like this, where we're talking about a percent. We're looking for the percent of raise, that percent will manifest itself as a decimal when we solve our equation, and then we change the decimal form into percent form. Remember, changing a decimal to a percent is nothing more than a matter of sliding the decimal point a couple of positions over and attaching that percent sign. So we've received a 12.5% raise here. Let's look at a number of word problems now by animation. And in each of these, sometimes the verbal model will be identified specifically, and sometimes it will not. But try to notice how the transition from the problem as it's written into the equation takes place. That intermediate thinking is what word problem solving is all about. How you go about thinking about going from the word problem to the equation. That's the hard part of solving word problems. Consider this problem. A shirt is reduced 15% for a sale. The sale price is $23.80. What was the original price of the shirt? Well, in order to solve the problem, we need to build an equation. And in order to build an equation, we'll write a verbal model. Now, that's simply our basic understanding of what's happening in this problem. Now, let's think about it. Notice that the sale price, we understand, is simply the original price less some discount. Now, what is that discount? How is that discount composed? Well, if we think about it a little bit, we'll understand that although we're told here in the problem that the discount is 15%, it really means that it's 15% of the original price. Now, that means, of course, 15% times the original price. So we have a hidden operation in this problem if we think about it a little bit. Well, let's see. Then that discount is some discount rate times the original price. Well, now that we have this verbal model, all we need to do is write some labels for the amounts that are in this equation and do some replacing. Well, let's see. Sale price, we're told, is $23.80. The discount rate is 15%. And we'll let X stand in for the original price. Now let's put these amounts into the equation. Sale price is $23.80. The original price, you see, is X. Now the discount rate is 15%. Original price, X. Now 15% is generally written as a decimal in problems like this. That's the working model for a percent, you see. And now we're ready to go with a solution. Well, in solving, we're going to collect the x's on the right, but let us understand that we have an understood 1x here. And that's kind of important to realize in order to collect the x's, because we're collecting coefficients. It's 1 minus 15 hundredths, which leaves 85 hundredths. So we have 85 hundredths x. Now what we do, of course, is divide on both sides by 85 hundredths to find x to be 28. Now we know that the original price of the shirt was $28. Consider this problem involving commission. A realtor works on a 6% commission. What is his commission on a house he sold for $95,000? Now, our verbal model here is simply a statement of how we understand the way that a commission is paid. We know that the commission is simply some percent of the selling price of the house. For this problem, we can see the amounts very clearly in the problem. The commission is 6% of $95,000. Now, we could have said that commission generally is some percent of the selling price, and then written the labels in here. Well, I have written the labels into our verbal model, at least in part. We have some replacement for the word is and for the word of, but we sort of build an equation as we're comfortable to do so in our problems. And in this way, we grow more and more comfortable with dealing with word problems. There's some latitude here, you see, in how we build our verbal model and how we build our equation. All right, let's continue with this one. Commission, is means equals. 6% is 6 hundredths. Of means times, and we bring down 95,000. Multiplying on the right, we find that the commission is equal to 5,700. And of course, that's $5,700. So we write our answer. His commission is $5,700. Notice one thing about this problem. We left the amount unknown as a word in this problem. And in some problems, that's perfectly okay, because after all, the letting a letter stand in for a word like this is simply a matter of convenience. We could allow the words to stand in if we want to, but it would make some more complicated equations a little too cumbersome to deal with. So we just let single letters stand in for them often, but the word is okay here.
Let's have a look now at a proportion problem. This is a classic proportion problem. We have a tree. We'd like to know the height of the tree. And it's inconvenient to climb the tree. But the tree is casting a shadow. And let's say that this tree is casting a shadow of 18 feet. Now, what we can do is compare the tree's height and shadow to the height and shadow of something known, like a yardstick. Yardstick is 3 feet tall, and let's say it's casting a shadow 2 feet long. Now, we're going to set up a proportion between the tree and the yardstick.
And we're going to call the height of the tree, well, let's say x. Now, the basis of this situation, of the proportion idea with the shadows and structures like this, is the notion that the sun is shining to cast the shadows, and that sun shines against the top of the tree and casts the shadow of the top of the tree like this, and in the same way it casts the shadow of the yardstick. And this angle that's formed up here and up here is identical on the two objects, so that the triangles formed are similar triangles. Now, similar triangles are triangles that have the same shape but are of different size. And similar triangles have the characteristic that corresponding sides are proportional. Now, so we're setting up a proportion here based upon the similar triangle idea. Now, all of that information about the triangles is perhaps unnecessary to the solution of the problem, but it's the background of this kind of setup. Well, here's what we're going to do. Since we have a proportional situation here, similar triangles and the proportional idea, we're going to say that the height of the tree corresponds to its shadow in the same way as the height of the yardstick corresponds to its shadow. Now, here's the verbal model. The verbal model is like this. We're building sort of a half equation, half word problem here. The height of the tree corresponds to its shadow, the shadow of the tree, you see, in the same way as the height of the yardstick corresponds to its length, the length of the yardstick. And then all we have to do, of course, is fill in our information. The height of the tree, we said we were going to let x stand in for that height. So x is to 18 as 3 is to 2. And then by cross multiplication, x times 2, 2x, 18 times 3, 54. Dividing on both sides by 2, we find x to be 27. So the height is 27 feet, and we haven't even had to climb the tree. Take a look at this problem. Here's one involving interest. Now, a lot of times word problems lend themselves well to a verbal model that is given by or suggested by some kind of formula. And here is such a problem. Suppose we have $10,000 in two investments, and suppose that one is paying 9.5% interest and the other is paying 11% interest. And let's suppose that $1,038.50 in interest is earned in 1 year. Now, how much is invested at each rate? How much is invested at each rate? We had $10,000 to invest, and how much is invested at each rate? Well, our verbal model consists of just looking at the problem and suggesting some statement of equality here, something that sort of makes sense, that gives a relationship of equality here. The interest that is earned at 9.5% plus the interest that's earned at 11% is equal to the total amount of interest earned. It almost seems obvious, doesn't it? The interest at one rate plus the interest at the other rate is equal to the total interest. And yet, this almost obvious statement here, which is half mathematical with the plus sign and the equal sign, and half word problem with these words involved, this verbal model leads us directly to our relationship to solution. Well, what is the interest earned at 9.5%? Well, the formula for interest is principal times rate times time. That is, I is equal to PRT. This is some interest, so it's some PRT. Now, we'll replace the P and the R and the T in just a moment, but this is some PRT, principal times rate times time. This is also some principal times rate times time, and the total interest we know to be $1,038.50. Well, all we need is some labels now for the items that are suggested here. Now, I'm going to put the labels in as I go. We would probably list them separately if I were doing this on paper, but the principal, the amount of money invested at this rate, let's let X be that amount of money. And that's one of the things that we're looking for here. Remember, we're looking for how much is invested at each rate. So X is the amount, let's say, that's invested at 9.5%. The rate, the interest rate, well, we were given that here. 9.5% as a decimal is 0.095. And the time, of course, we were told was 1 year. So here's our PRT for this part. Now, the principal times rate times time here. Now, here's the part that is not obvious in this problem. It is to represent the principal amount that was invested at 11%. Now, remember, we had $10,000 total invested in these two investments, and X amount of dollars were invested over there. Well, how much is left to be invested at 11%? See, that's really how we need to think about it to arrive at this idea. The representation of the principal invested at 11% would be the $10,000 investment overall minus the amount invested at the other interest rate. You see, so 10,000 minus X is the amount invested at 11%. All right. Now, the rate, of course, is 11% or 11 hundredths, and the time, of course, 1 year is equal to $1,038.50. Now, the important thing here, we're not going to belabor this and go through to a final solution. I'm confident that we can solve this from this point. The important thing here to emphasize is that we went from a verbal kind of problem, the problem written out, into a verbal model, sort of a model for the equation, and went into an equation format, making use of a formula here, a part of a formula. Interest is principal times rate times time. You see, it's an interpretation all the way down to where we have an equation to work with, and we solve the equation, and we have our answers.
Here's a typical proportion problem. If 40 pounds of fertilizer are used on 2,400 square feet of lawn, how many pounds of fertilizer are needed for a lawn of 5,400 square feet? Now, with proportion problems, the format is pretty well established. We're setting up a ratio or a comparison of two items on one side of the equation and the same two items on the other side. In this case, we're comparing pounds to square feet on one side and then pounds to square feet on the other side. Now, in writing this kind of relationship down, we are really establishing our verbal model for this particular kind of equation. Well, let's fill into our verbal model with some labels. Well, let's see, pounds to square feet. For the first part of the problem, we had 40 pounds comparing to 2,400 square feet. Now, on the right side, we're looking for some unknown number of pounds of fertilizer that compare to 5,400 square feet. So let's let a letter stand in for those numbers of pounds. So we have X over 5,400 on the right side. Now it's a matter of solving the equation. Well, let's move our problem up to the top. And the fast way, you know, is to cross-multiply. If we cross-multiply this way, X times 2,400, we get 2,400X. Cross-multiplying the other way, we get 40 times 5,400. Now, multiplying on the right, 40 times 5,400 is 216,000. Well, now our prescription would tell us to divide on both sides by 2,400. Dividing on the left, of course, will give us the nice cancellation. And dividing on the right, we find X to be equal to 90. Now, since we were looking for the number of pounds of fertilizer, this is 90 pounds. And now we can write our answer as a complete sentence. 90 pounds of fertilizer are needed. Here's another proportion problem. On a certain map, 1 inch represents 35.5 miles. What distance is represented by 4.7 inches? Now again, what we intend to do in setting up our proportion is write a comparison of two quantities on each side of our equation. Now in this case, you notice we have inches compares to miles on each side. We could be writing this as miles over inches as long as we write the same sense of our proportion on both sides, that is, miles over inches on both sides of our equation. Now, notice also that both of these are distances, but there's a major difference between these distances, isn't there? Because the inches represents a distance on a map, whereas the miles represents distance along the countryside. Well, let's run through our problem here. The first part of it says that 1 inch represents 35.5 miles. So in our proportion, we write 1 compares to 35.5. Now on the right side, we're asked for the distance that is represented by 4.7 inches. So on top, we write 4.7, and on the bottom we'll write a letter, something like N perhaps. Now to solve, of course, we'll cross multiply. 1 times N is N for one cross multiplication, and the product along the other diagonal is 166.85. And really we're finished here, but let's understand what N stands for. Notice that the bottom of our right side fraction was some number of miles, so this is 166.85 miles. And we can write our answer. 166.85 miles is represented by 4.7 inches on the map. Here's a problem that involves a formula. A savings account of $2,300 is left for 90 days drawing interest at a rate of 7%. How much interest is earned, and what is the amount in the account at the end of 90 days? Now, when a formula is indigenous to a problem, the formula often takes the place of a verbal model. That is, the formula becomes the verbal model. In this case, interest is equal to principal times rate times time. And the labels are sort of built in, aren't they? Because we can simply write this as I is equal to PRT. Now, plugging in directly, we know we're looking for interest, so we'll bring down I. P, the principal, is the amount of money invested. In this case, $2,300. R is the rate of interest, and it's 7%, which we write in our equation as 7/100ths. Now, 90 days. Now, note that the rate of 7% implies 7% per year. Now, that means that the time has to be expressed in some portion of a year, some number of years or portion of a year. In this case, 90 days, we write as the fraction 90 over 365, because that's the fraction of a year over which this money is earning interest. All right, now we're ready to go through and solve and do the operations that are implied. 90 over 365 is this decimal. Now, when we multiply the factors here, we find I to be 39.698. Now, we need to round this into some dollars and cents pattern, which means we'll round it off to the nearest hundredth, you see. So we can say then that the amount of interest earned in 90 days is $39.70. Now let's turn our attention to the B part of the problem. What is the amount in the account at the end of 90 days? Well, the amount in the account is the original investment into the account of $2,300 plus the interest that has been earned over that period. So we simply take the principal and we add the interest earned. So we have $2,339.70. The amount in the account at the end of 90 days is $2,339.70. This one also involves the interest formula. A small airline company borrowed $7.5 million to buy some new airplanes. The loan rate was 15%, and the airline paid $562,000 in interest. What was the length of time of the loan? Now, notice in this one we're looking for something other than interest, but still, as our verbal model, we use the formula I is equal to PRT. We simply do a different kind of replacement into it. We replace the letters with amounts that they stand for. I, of course, is the amount of interest, and we're given that as $562,000. Principal, the amount of money borrowed in this case, $7.5 million. Rate, the rate of interest, 15%, which we write as 15/100ths. And we bring down time. We'll let T stand for time in this case. Well, on the right, we multiply $7.5 million times 15/100ths and get $1,125,000. Now we bring down T, of course, and our prescription next would call for us to divide on both sides by the coefficient of T. In doing so, notice the decimal we get on the left side of the equation. On the right, of course, we get T. Now that decimal, 0.4995556, is very, very close to 0.5, isn't it? And we're talking about a portion of a year here. So we're talking about a half a year, or the term of the loan was 6 months. This problem involves compounding interest. Suppose that $50,000 is invested in a savings account for 3 years and the interest rate is 8%. How much money is in the account at the end of the 3-year term if the interest is compounded annually? Well, compounding interest means adding the interest earned to the principal and having that amount earn interest. Well, because the compounding is done annually, we'll divide our problem into 1-year increments. In year 1, let's see how much interest is earned. The interest is the principal that we start with of $50,000, an interest rate of 8% or 0.08, and the time, of course, for this 1-year period is 1. Well, multiplying, we get 4,000. So the interest after 1 year is $4,000. Now, let's look at a chart here. Let's build a chart to understand what's going on. In year 1, we start with $50,000. We earn interest of $4,000. So at the end of the first year, we have $54,000. Now, the idea of compounding is that at the beginning of year 2, we're starting with $54,000 that will earn interest. Let's go back to our worksheet now. Year 1, here's what happened. We earned $4,000 in interest. Now, in year 2, we use the same formula, except this time our principal, the amount we're starting with, will be, instead of $50,000, it'll be $54,000. Now, the rate and time are the same as they were before. So in year 2, we earn $4,320 in interest. Well, let's go back to our chart. The interest earned in year 2, $4,320. Now, adding that to the amount we started with at the beginning of year 2, we find that the total that we have in the bank at the end of year 2 to be $58,320. That, then, is the amount of principal that we start year 3 with. All right, here we go, back to year 3. We use the same relationship, I is equal to PRT. We replace the principal with, $58,320. The rate and time remain the same. Now we find the interest earned in the 3rd year to be $4,665.60. Let's add that amount into our chart. So the interest in the 3rd year is the amount that we just found. So the total in the account at the end of 3 years is $62,985.60. Let's turn our attention now to a distance problem and concentrate simply on setting up the equation to solve this problem. The problem says a group of students plan to take 2 cars to a soccer game. The first car leaves on time, travels at an average speed of 45 miles per hour, and arrives in 3 hours. What average speed must be obtained by the students in the second car if they leave 1/2 hour after the first car and arrive at the same time as the first car? Well, it may sound a bit complicated when first reading this problem, but if we set it up in a particular way, it becomes very simple. Now, one thing to notice about the problem is that the second car leaves 1/2 hour after the first car. If the first car is traveling for 3 hours, the second car then will travel for 2.5 hours. All right, another thing that we're looking for here in order to set up a verbal model is some condition of equality. Now, notice that the cars are leaving from the same place and they are going to the same destination, to this soccer game. So the big picture here is that the distance traveled by the first car is equal to the distance traveled by the second car. And that can become the basis upon which we build our relationship for solution. All right, so distance traveled by one car is equal to the distance traveled by the other. Now, what do we understand about distance? We understand that distance is equal to rate times time, which indicates that distance can be replaced by rate times time. So the distance traveled by each of these cars can be thought of as some rate times time. All right, now what do we know from the information in the problem? We know that regarding the first car, the rate was 45 miles per hour. The time was given as 3 hours. So on the left side of the equation, we can write 45 times 3. Now, what about the second car? Well, we were told that the rate is unknown to us. That's what we're looking for, so we'll let R stand for the rate of the second car. Now, the time, as we mentioned, is 2.5 hours, that traveling time. It was they left a half an hour later than the first car, and they want to arrive at the same time, so their travel time is 2.5 hours. Therefore, we can replace in the right side of our equation with r times 2.5. Now, this is the setup to solve the word problem. And we won't go through to a final solution here because it's really this thought process that allows us to set up the equation that we want to concentrate on here. Here's another problem involving distance, rate, and time. A freight train travels 100 miles in the same time that an express train travels 150 miles. If the express goes 20 miles per hour faster than the freight, find the rate of each. Now, we're looking for some statement of equality here. And notice in the first sentence it says, in the same time. Now, that's going to be an important matter for us in building a relationship here. Let's summarize our information. The freight goes 100 miles in the same time, it says, as the express goes 150 miles. All right, and we're also told that the express goes 20 miles per hour faster, and we're looking for the rates. Well, sometimes with distance problems like this, it's valuable to build some table of information like this. Now, let's fill in the information that we know. We know that the freight is going a distance of 100 miles, the express is going a distance of 150. Let's express the rates. Now, the rates are what we're looking for. If we let R stand for the rate of the freight, then R plus 20 would be a representation for the express rate because the express is 20 miles per hour faster. All right, now we note that the times are equal to one another. We don't know what that time is. We simply know that they are equal. So our concept here is that the time traveled by the freight is equal to the time traveled by the express. So time is equal to time is our fundamental concept here. Now let's consider how we might rewrite time in terms of distance and rate. You know, from the distance formula, distance is rate times time, we can re-express time as distance divided by rate. Now we have an equation that we can plug into. Now notice on the left we're talking about information about the freight, and on the right, information about the express. Of course, the distances are given up in our chart there. The distance for the freight is 100. The distance for the express is 150. Now, on the left, we would leave the rate as simply R. So we have no replacement to do there. But on the right, the rate of the express is R plus 20. Well, now we're ready to solve our equation. Now, I'm going to solve the equation a little bit differently. You know, in the past when we've had a single fraction on left and right, what we can do is cross multiply, and that is a rather rapid way to work this problem, but just for variety, what I'll do is decide to multiply on both sides by a common denominator, R times R plus 20. On the left, the R's, of course, would cancel, and we'd be left with 100 times R plus 20, or 100R plus 2,000. On the right, we get the cancellation of the binomials, and we have 150 times R. Now we would subtract 100R on both sides, and the equation would look like this. Then collecting on the right, we get 2,000 is equal to 50R. Dividing by 50, we find that R is 40. Now we're ready to write our answers. We know that R stood for the rate of the freight, so the rate of the freight train is 40 miles per hour, and the rate of the express train is 60 miles per hour. As we read through this problem, see if you can find a fundamental concept of equality. A small plane has a speed of 170 miles per hour in still air. Find the speed of the wind if the plane travels a distance of 400 miles with a tailwind in the same time it takes to travel 280 miles into a headwind. You see, what we want to concentrate on here is some condition of equality. And because if we try to solve the whole problem at one time, it becomes very complicated. One way to view it is like this. Let's just outline the information that we have here. We're told that the plane can travel 170 miles per hour in still air. So we pick up on that idea. We pick up on the idea that we're looking for the wind speed. But the most important thing is this idea that the plane can go 400 miles with the wind in the same time as 280 miles into the wind. Well, let's put this information into a table of information. Okay, here's our table. The first thing we want to do is represent the unknown quantity here. Let x represent the wind speed. Now, x is the wind speed, but the speed of the airplane going with the wind is certainly not the same as x. It's 170 plus x. It's the speed of the plane in still air plus the wind speed, since the wind is helping the airplane go faster. Going against the wind, it's a similar kind of thing, except the wind is working against the airplane speed, so we represent the rate against the wind as 170 minus x. Now, the distances are given to us as 400 with the wind in the same time as 280 against the wind. And understand here that the times are equal to one another, with and against the wind. Now, that idea of the equality of time gives us the fundamental concept in our problem. The time going with the wind is equal to the time going against the wind. Now, we learned earlier that time can be represented as distance divided by rate. Now, notice on the left side, the distance divided by rate. The distance and rate are given up in our chart. So we fill into that side of the equation with 400 over 170 plus x. And on the right, 280 for the distance and the rate 170 minus x for the denominator. Now we're ready to solve our equation. Let's solve by cross multiplication. Multiplying in this direction, 280 times 170 gives 47,600. And 280 times the x gives 280x. Multiplying along the other diagonal, 400 times 170, 68,000. 400 times the negative x is negative 400x. Now the next part is rather interesting. We understand that we're going to place the x's on one side and the constants on the other side. Of course, when we add 400x to both sides, the negative 400x will disappear on the right and make an appearance on the left. We also understand that when we subtract 47,600 on the left, it'll make its appearance as the negative of 47,600 on the right. All right, now let's collect the x's on the left, and let's collect the constants on the right. We'll get this equation. Now, the next thing we want to do, of course, is divide on both sides by 260. We get a nice cancellation on the left, and on the right, when we do the division, we find x to be 30. And that, of course, was the speed of the wind, and it's 30 miles per hour. So we simply write our answer. The speed of the wind is 30 miles per hour. Consider this problem. Tickets for a concert were $15 for each floor seat and $10 for each stadium seat. There were 800 seats on the main floor, and these were sold out. If the total revenue from ticket sales was $52,000, how many stadium seats were sold? Let's outline our information. We're told that the total revenue is $52,000. The price for every floor seat is $15. The number of floor seats, 800. The price per stadium seat, $10. The number of stadium seats is what we're looking for. Now, notice that we're really creating labels for information that will go into a verbal model here. It almost seems like we're taking things out of order because in the past we have built the verbal model ahead of time and then created the labels. It really doesn't make any difference. It's a matter of whatever you're comfortable with. This way of doing things allows us to outline our information and sometimes helps us to understand the problem a little better and build the verbal model a little more effectively. Now, notice what we have here, total revenue. A lot of times when the word total is used, it's a hint as to how we approach the problem. In this case, the total revenue, it makes sense, is equal to the revenue from the floor seats plus the revenue from the stadium seats. All right, let's fill in the information that we know here. The total revenue we know is $52,000, so we'll plug that in. Now, the revenue from the floor seats is really the price per floor seat times the number of floor seats. So it's 15 times 800 here. In a similar way, the revenue from the stadium seats is the price per seat times the number of seats. Okay, let's solve our problem. Now, 15 times 800 gives us 12,000. Subtracting 12,000 on both sides gives us this. Collecting the constants on the left, we get 40,000. Now we want to divide on both sides by 10 to find x to be 4,000. Now this tells us that, remember, x stood for the number of stadium seats. That's what we're looking for. So we say then that 4,000 stadium seats were sold. Here's a mixture problem. 50 gallons of 70% acid solution are obtained by mixing an 80% solution with a 50% solution. How many gallons of each solution must be used to obtain the desired mixture? Now, it turns out that we build an equation from a verbal model which is emulated by the mixing process itself. That is, if we can imagine these two liquids being mixed together, we're really building a verbal model and therefore building an equation. Now notice if we take some 80% acid and some 50% acid, mix them together, which is what this problem is saying, what we get as a result is 50 gallons of liquid, which is 70% acid. So now if we put that idea into equation form, that is, some liquid plus another liquid is equal to 50 gallons of 70% acid, then we're building our verbal model. All right, if we let X stand for the number of gallons of that first container of liquid, then the next container of liquid can be represented, the number of gallons can be represented as 50 minus X. Now that's important, to represent the number of gallons in the second container correctly. Well, now let's indicate the percent acid involved in the two solutions being mixed. We know from earlier that 80% acid was in one container and 50% acid was in the other container. Now, it turns out that our equation is based upon the amount of acid involved in each of these containers. That is, the amount of pure acid in the first container plus the amount of pure acid in the second one is equal to the total amount of pure acid. And that amount of acid is found by multiplying some number of gallons times the percent of acid. Now, that's true in every case here. Now, notice that gallons times percent plus the gallons times percent is equal to the total gallons times the resulting percent. And that's the way we build our equation. So here's our verbal model, and here comes our equation. X number of gallons times 80% plus 50 minus X number of gallons times 50% is equal to 50 gallons times 70%. And all of this is from the information below the equation. Well, let's go on to solve the equation. Now, what we're going to do next is write 100 times each of the terms here. Now, notice I'm doing this in order to clear the decimals. If I simply multiply 100 times each of those percents or each of those decimals, it'll simply slide the decimal points 2 places to the right, and now we can deal with whole numbers instead of the decimals. Well, let's continue. X times 80 is 80x. 50 times 50 minus x is 2500 minus 50x. And on the right, 50 times 70 is 3500. Of course, we'll want to collect the x's on the left and throw our constants to the right. And when we do that simplification, we find that 30x is equal to 1,000. Dividing on both sides by 30, we find x to be 33.3. Now remember that x represented the number of gallons of the 80% acid solution. And in the other container, we represented the number of gallons by 50 minus x. Well, x in this case we just found to be 33.3. So 50 minus 33.3 is 16.7. Now we can write our solutions. We know that 33.3 gallons of the 80% acid solution and 16.7 gallons of the 50% acid solution are needed.
Idea when we have factors, like in this case, if the product of these two factors, you see, is 0, then it must be the case, for this to be true, that either this factor is equal to 0 or that factor is equal to 0. Now, if this factor is set equal to 0, then x is equal to 2 to cause this to happen. It's like we're saying, gee, what value of x will cause this factor to be equal to 0? What makes x minus 2 equal to 0? Well, when x is 2, this factor becomes 0. And in a similar sense, what value of x causes this factor to be 0? And the request is made through a little linear equation, you see. And when x is equal to negative 3, this factor becomes 0. So we're looking for, in the idea of solution is that we're looking for a value of the variable, in this case x, that causes the equation to be true. And the equation is true when one or the other factor is 0. So these are indeed values of the variable that cause the equation to be true. Well, notice the structure now of this idea of solving by factoring. That is, we have factors on one side of the equation and 0 on the other side. That's an important idea, that 0 is on one side of the equation by itself. Here's a case in point. Suppose we have this equation. Now notice 3 is over here. Even if we could factor this polynomial, it wouldn't do us a great deal of good in finding a solution. What we have to do first is take the 3 and remove it from the right side. That is, subtract 3 on both sides. And of course, when we do, we'll get 0 on the right as expected. And when we subtract 3 from 7, we get 4. Well, now we're ready to go through the factorization process. When we factor the polynomial, we get these two factors. Now, we're asking ourselves the question, what value of x causes this factor to be 0? And the question can be posed in a linear equation format. What value of x causes this to be equal to 0, you see? And solving, we find x to be negative 1/2. here we're asking ourselves what value of x causes this factor to be 0. And clearly x needs to be -4. Now this one, sometimes by observation we can just see the amount for x that would cause the factor to be 0. Here we could see that -4 plus 4 would cause this to be 0. You see, so we wouldn't have to write down the little linear equation each time. But when the factor becomes a little more complicated, as in this case, it's helpful to write the little linear equation. Here's a situation involving multiple factors.